Good morning, class. Today we're going to be continuing our notes over the atmosphere. Remember that we're working on this pretty lengthy standard, and we're focusing during these notes on a certain I can statement. You should be able to identify the major source of energy for wind, which is also known as air currents. Alright, so the sun's energy and its role in air currents. It all starts from the sun giving off or emitting electromagnetic energy. In simpler terms, light energy. And light, as a simple term, there's different light waves. Some have a longer wavelength, which we'll be talking about later on in the year, and some have a shorter wavelength. So when we're talking about what kind of light comes from our sun, most of it is in visible light form, which is the colored part of the spectrum that you see right here. And the rest of it is in the infrared. There's very little UV that actually comes from the sun, but there is some. About 50% of all of the electromagnetic or light energy that comes from the sun is either absorbed by the Earth's atmosphere or it's reflected. So right here, if you look at this, 25% of the sunlight that is shining from the sun towards Earth, it is reflected by the clouds and other dust and gases in the air. Another 20% of that sunlight that comes towards Earth is absorbed by gases and particles in the atmosphere, so it actually absorbs it, changing that into heat energy. And then about 50% is collected by the Earth's surface, and therefore is turned into thermal energy to heat the Earth's crust and also the water that is on Earth's crust. And some of that radiates back into the atmosphere. Greenhouse effect. What is it? I'm going to click on this to kind of give you a brief overview. So we're going to watch a short video during these notes. Here we go.
Did you know that gases in our atmosphere help control the Earth's temperature? Greenhouse gases, like carbon dioxide, trap heat in the atmosphere and keep the Earth warm. This is called the greenhouse effect. It all starts with sunlight, which is a form of energy. Land and water absorb most of the sunlight that reaches the Earth. The rest is reflected back to space. The Earth's surface warms up, then gives off energy in a different form, called infrared radiation. This energy travels back towards outer space. Greenhouse gases trap some of this energy in the atmosphere before it can escape, making the Earth warmer. We need some greenhouse gases. Without them, our planet would be too cold for plants and animals to live. But people are adding extra carbon dioxide and other greenhouse gases to the atmosphere. Whenever we drive a car, use electricity, or make a product in a factory, we use energy. A lot of this energy comes from burning fossil fuels, like oil, gas, and coal, which produces carbon dioxide. How do you think extra greenhouse gases affect the amount of heat trapped in the Earth's atmosphere? You guessed it! Extra greenhouse gases trap more heat, which makes the whole planet warmer. And warmer temperatures lead to effects like changing rain and snow patterns, rising sea level, melting glaciers and ice sheets, and much more. It's a big problem, and it's all happening because we are overloading the atmosphere with greenhouse gases. By making the greenhouse effect stronger, we're upsetting the Earth's natural balance and warming our planet.
Okay, so a short video clip, again, to just kind of give you a brief overview of the greenhouse effect, and it also goes into one of the topics that we're going to be doing an article review on, which is global warming. So basically, when the Earth's surface is heated, it radiates some of that energy back into the atmosphere, and some of that radiated energy is trapped by our atmosphere. And scientists sometimes refer to the greenhouse effect as the Goldilocks effect, because our atmosphere traps in just enough heat energy to keep us warm enough, but not too warm. Venus and Mars, Venus is way, way, way too hot. Mars is way, way, way too cold. So due to their differences in atmosphere, they have less of the Goldilocks effect with their greenhouse. Comparing commonly used terms when discussing the atmosphere. Here are some terms that people don't necessarily know the definitions of a lot of times, so when they're using them interchangeably, sometimes that can cause confusion. Thermal energy is one of your vocabulary terms. It is a measure of the total movement of particles in a substance. And temperature is a measure of the average movement of particles in a substance. So if you think about those as math terms, total means that you are collectively adding up, finding the sum of all the movement of the particles. But the average means that you are finding the movement of each particle, adding those together, and then dividing by however many particles are there. So if you think about your body temperature, when we take our temperature, we are finding the average movement of particles within our body that gives us that temperature. Okay? We know that if our temperature rises, there's a lot more going on with our body repairing itself. And if our body temperature gets too low, then that means that our body is the particles inside it are not reacting as quickly as needed to keep up with the bodily functions. Heat is defined as the transfer of thermal energy from one substance to another. So how that thermal energy is passed is considered heat. And there are 3 types of heat transfers. The first one we're going to talk about is radiation. Actually, I think we're going to talk about conduction first, and then radiation, and the last one will be convection. Conduction. It's the transfer of thermal energy, all 3 are, between neighboring molecules in a solid or between 2 solids that are neighboring. So this occurs when there's a temperature difference. So if there is a temperature difference within a substance, then the particles will react in a way that spreads that thermal energy throughout the substance to make it a more balanced temperature, and the thermal energy spread throughout it will be more balanced. All right, so energy also transfers from always, and this is something you just need to know. We've talked about how air pressure always moves from a higher pressure zone to a lower pressure zone, and thermal energy does the same thing. So when there's an area of higher thermal energy, which means probably an area of higher temperature, then that energy will transfer to an area of lower temperature. And I want you to consider right now a piece of melting ice. We all know what melting ice in our hand feels like. So it feels extremely cold to us. And observations also, not only feeling the cold, but also seeing the ice melt in our hand. What's going on here? What's truly going on? Well, your hand has a higher temperature, okay, which means that the average particle movement is much higher than what's in the ice cube. Therefore, that energy is going to transfer from an area of higher temperature to an area of lower temperature. And in doing that, your hand's temperature is going to drop, and the ice cube's temperature is going to increase. And this will help equalize the temperature between the 2 different. I'm going to click right now on a visual that kind of shows this. Here is a solid that there's heat placed on top And you can see that as the heat is being transferred throughout the solid, that the particles are moving faster and faster and faster. And those are bumping each other, causing more to move fast and slowing the ones down that just bumped into them. So it kind of spreads out this heat energy throughout the substance. All right, back to the PowerPoint. So now we're going to talk about radiation. Radiation is the heat transfer through empty space. An example of this is actually the sun's electromagnetic energy coming through space to Earth. Much of that area that the electromagnetic energy is traveling through is empty space, similar to a vacuum. So it does not require any movement or bumping of matter like you just saw in that demonstration of the particles bumping into each other as the heat energy was traveling through it. So all objects actually can radiate energy in infrared form as long as they are above negative 273 degrees Celsius. So even though we feel like a object is very cold, it actually is still giving off some heat energy. And some things, not all, do glow when they give off heat energy in the form of radiation, and these are examples would be a fire or the sun. Convection. Now this is the one we're going to be focused on over the next several days because it has most to do with what we're going to be talking about in the atmosphere, although all three have to do with heat in the atmosphere. So this is a transfer of thermal energy in fluids. Fluid can be a liquid or a gas. Some people get confused by that. Our atmosphere is mostly gases. Also includes some liquids and solids though. So our atmosphere acts a lot like the air in this diagram within a room. Now here's a radiator. A radiator are often found in older homes and they give off heat, okay? So this heat will heat up the air particles in this area here. As the air gets hotter, the particles are moving more, they spread out more, becomes less dense, and the air rises. As it reaches the top of the room, it kind of hangs out at the top of the room until it begins to cool because now it's gotten away from its heat source. So the air then again starts to fall and drop, creating this circular motion in the room, becomes even colder and it's traveling along the floorboard. Now it's that dense, high pressure air, and so therefore it is going to get heated again by the radiator, become less dense, lower pressure, and it's going to rise again. So that is very similar to how the atmosphere acts as well. I would like you to take a moment to use this diagram to map the heat transfer from the sun to Earth's atmosphere. There are 3 blanks left on your diagram or on your notes to fill in.